So the big change in Unit 4 is we've created the particulate model in Unit 1. Okay? We've talked about interactions, intermolecular forces, and physical properties. We talked a ton about physical properties. Now we actually get a chance to talk about chemical change. So we're going to move beyond the physical properties and talk about chemical change. We're still going to use this microscopic representation that we've been using, the particulate model, to look at chemical change because it's incredibly useful, it's incredibly important, and powerful. But now we're going to also look at reactions. Okay? So the next step is to look at how structure not only dictates function, but dictates chemical reactivity. That's where we're moving in today. So how, when, and why do substances interact to produce new substances? But for nylon synthesis, there are two chemicals that form a barrier between. They're not immediately miscible. Okay? And at the interface, the reaction takes place. You can literally take a little bit of the interface, pull it up, and what this is just a paint roller with a paper towel roll and a chopstick, and you turn it, and literally as those two interfaces happen, the nylon pulls out of the interface. Okay? So we're going to be looking at chemical reactions. So this unit, how do we model chemical change using a particulate model of matter? We're going to look at using the case studies we're going to do, making new materials, looking at air pollutants, and also figuring out fuels. So when you, what's cleaner to burn? Graphite, coal, ethane, methane, natural gas. Is it better to burn fossil fuels? What kind of energy do you get out? What happens with the little pollutants? So coal is really great, but it's not necessarily clean because there's lots of sulfur mixed in it. And when you burn it, you get sulfur compounds with oxygen as well. I also want to think about what about the ratios? Okay, so why do engines have carburetors that infuse oxygen into the mixture of fuel when you burn? How much oxygen do you need? Well, we don't have oxygen tanks in our car. We have air. So what percentage of air is oxygen, and how much do we need to pump it in? These are the kinds of questions we're going to be looking at. Okay? And we're going to use those case studies to look at this change. So here really are the essential questions for this unit. Okay? And we're going to put some names to them. So how much of a substance do I need in order for the reaction to occur? Anyone have any ideas of what that could be? Oh, I heard it. Stoichiometry, right? How much of a substance do I need, or how much do I get? It's all stoichiometry. How many oxygen molecules are needed to burn ethane? How many oxygen molecules are needed to burn octane or coal? Okay, that's stoichiometry. Any ideas about how much energy do I need or get? Think about the model we had, right? We had the unmixed material, and now the mixed material is up here. Okay, did that take energy? We had to put energy to go from unmixed to mixed? Yeah, that took energy. Or if I mixed them together, did you get energy out? Okay, so this is called thermochemistry. Okay. Does the reaction happen spontaneously? Okay, how fast is the reaction? Anyone know what a term for that is? Kinetics. Okay, is it an instantaneous process? And then to what extent does the reaction take place? Right? So think about a dance hall where you have individual people come to the dance hall. If you think about over the course of the evening, they form couples, right? Okay. To what extent does the coupling happen based on the music that plays, right? Oh, we're all just friends. Real easy poppy song. Everybody's on the dance floor. Slow dance. Oh, shit. Right? Oh, another good poppy dance. YMCA. I'm going to get back on the floor. Oh, I really like you when I'm dancing. I'm going to leave with you and form a product. What's that process? Yes, thermodynamics, okay? So, to what extent does it happen? Will it happen? We talk about equilibrium processes. That all gets into thermodynamics, okay? So how do we explain it? How do we control these? How do we predict it? The first module, we're going to talk mostly about stoichiometry. Okay, we're going to do a big, broad overview of these ideas, but we're going to spend a lot of time on stoichiometry. So that's where we're starting today. And again, we're going to use these models, ones that make pollutants and also processes that generate energy to look at chemical change. Because everybody, it doesn't matter your major, everybody uses fuel. We're in this room. Clearly, they're using a lot of energy to heat it today. I'm going to try to get them to change it because it's like everybody's falling asleep. So module 1 is about modeling and connecting. Like, how many people have balanced chemical equations in high school? Okay, right. Everybody has had that experience, so nearly everybody. Now, how many people have drawn out the particulate model to explain chemical reactions? Okay, a couple. So you had really excellent high school preparation. So this is what I want to do, is connect that particulate model, pressure, temperature, volume, all that stuff, solubility with chemical reactivity. So we're going to build this model to make it strong, so when you get to Dr. Berger's class, you got it up here. Okay? Or when you get to Dr. Lee's class, it's all there. So this is 2 ways you can look at chemical change. Okay? So formation of one or new chemical substances. Okay, great. Yeah, that's word, but what the heck does it mean? Okay? I can't look at a reaction and say chemical changes happen. Or can I? What observations can I use to say a chemical reaction is taking place? Any thoughts? What observations in the lab can you write down in your notebook to say, oh, something must be happening because I see, insert, yeah. Change in color, absolutely. Yes. Bubbles, formation of a gas. Yeah. Change in temperature, heat is given off or heat is taken in. These are all observations that tell you a new chemical substance was formed. Absolutely, yeah. The other. We've got gas, we've got bubbles, we've got heat. Okay, we're going to do more of these, but think along those lines. Okay? The change in the net amounts of some chemical species. How could you say there's a change in amounts based on those kinds of things that we just said? Bubbles, or heat, or not heat, big heat. How can you relate that to amounts? It's a simple extension. So Jay, what was yours? Color, okay? So how much color is being found, right? So how much, let's quantify it. How much heat, how much gas, how much color, how much solid, right? So the amounts of the chemical species that are formed as well. So those are things we're going to look for. So let's look and see if you can connect observations to tell me if a chemical reaction is taking place in this video. Okay? What are the signature features that characterize the chemical processes for this reaction? So I'm going to turn this up. I know it's kind of quiet, so let me know if you can't hear it. I'll turn it up.
In the reaction of the solutions of lead nitrate and potassium iodide.
Lead nitrate and potassium iodide. Lead nitrate. Is lead nitrate soluble in water? Lead is, well, nitrate is nitrate's -1. Okay, -1. And lead is +2. Is that soluble in water? Yes, lead nitrate is soluble in water. And potassium iodide. Iodide is charged -1 potassium, +1. Is that soluble in water? Yes. And the reaction, okay, we looked at this.
In the reaction of the solutions of lead nitrate
Soluble.
and potassium iodide,
Soluble.
2 compounds are produced. One is aqueous potassium nitrate, and the other is solid lead iodide, which precipitates from the solution as yellow particles.
So what do you see? Changing color. What else do you see? The potassium nitrate. No, potassium nitrate, she said it was aqueous. Right? The chemist said it was aqueous. So what are we seeing here? We see yellow color, but what are we actually seeing? Yellow lead nitrate. Okay? Yellow lead nitrate or yellow lead iodide. Okay? Lead iodide is a precipitate that has a yellow color that you can see. So in this case, it's not just a color change. It's a color change where the color is associated with the new precipitate that forms. Okay? So those are some chemical observations. And if you held it, you could check and see if the temperature changed as well. Okay, so chemists sat down and they looked at all these different signature features, and there's some common features of all chemical reactions. Okay, so got to start with something. Put these in your own terms to make it more powerful. Okay, you got to start with something. We call them reactants. You got to end with something. We call them products. Okay, and mass is conserved. We don't lose anything in the process. Everything's still there. Okay, so mass is conserved. So see if you can find these three features, signature features, in the next two examples. Okay? Link your observations to what you see. Okay? Call out, and for each of these two videos, I want you to tell me the reactants, the products, and how you could tell that mass is conserved, or what you would have to do to show that mass is conserved. Everybody okay? Ready?
When we put magnesium metal into
Magnesium metal,
aqueous hydrochloric acid,
aqueous hydrochloric acid,
the two react. Aqueous magnesium chloride is formed along with gaseous hydrogen.
So what would I have to do to that reaction? Okay, so what's the reactants? Magnesium metal, aqueous hydrochloric acid, products, magnesium chloride, and hydrogen gas. Do you see a color change? No. Do you see a precipitate form? No. We're not there to check the temperature. So how do you know if chemical reaction is taking place if they didn't tell you that? What would you observe? Hydrogen gas. So bubbles. This is a gas form. Okay? So you have to, in this case, what we're always doing is looking for one of the reactions, one of the reactants, either reactants or products, okay, that either changes color, changes state. How would I have to prove that mass was conserved here? You have to gather the hydrogen gas as it comes off. Right. So maybe we could design a new reaction in order to prove mass balance, where perhaps I have magnesium metal in a balloon. That's all the air is out. Weigh it, right? Weigh it like that, and then move the balloon to dump all the magnesium metal into the gas, and then have the balloon fill up, and then weigh it again. Okay? That would be one way. Let's look at the next reaction. Again, starting materials, products, mass balance.
When pieces of aluminum foil are placed in a beaker containing bromine, a violent reaction occurs. The elements react to produce aluminum bromide, which consists of 2 aluminum atoms for every 6 bromine atoms. It is visible as a white powder deposited on the beaker.
Okay, I should probably turn off the volume. So what are the starting materials here? Aluminum foil. So what form of aluminum is that? Solid to metal. So it's in the atomic form of aluminum. Bromine, BR2. It's also in the atomic form of 2 bromines together, covalently bound. And the product, anybody catch it? Aluminum bromide. So what was the formula for that? Anybody catch it? Al2BR6, yes. Okay? So, and that's what this white solid is. So some reactions give off a very violent, vigorous. There was some literature just in the last 2 weeks about how students in a big university were hurt because an instructor had mixed, so it's called a thermite reaction. You take iron and rust, and in high school, have you seen thermite before? You take rust and aluminum, you mix them together with a little acid, and they usually do it in a clay pot. And underneath the clay pot, you're supposed to put sand to catch what falls. What happens is you mix it together, and just like this, it takes a couple seconds, but then blows up and gives off enough heat to melt the iron, and you get molten iron coming out the bottom of the clay pot. You can Google it. Okay? Thermite. We're not going to do it here. We don't have the equipment. We're not equipped with the proper safety equipment to do that now. Oh my God. Yeah. Yeah. That's the kind of professor that shouldn't be a professor.
He still is.
Yeah. That's crazy.
2 incidents could be
Yeah, that's nuts, because that's totally avoidable. So if you don't have, what happened in this class was they didn't have sand at the bottom to catch the molten iron that was coming out. I mean, it looks like lava is pouring out of this pot. When they collected it in the sand, it hits the sand and it's okay. But it hit water, and then it was so hot it just spewed everything and jumped out at the audience. So, yeah, that's not an example of green chemistry. Okay, so a fourth signature feature of reactions. Thermite is a perfect example. Okay, thermite is, did that give off energy or take in energy? Give off. The one I told you that melted. It gave off enough energy to melt iron. Okay, so it probably got up to about 1,000 or 2,000 degrees. So that is an exothermic, give off energy. Exothermic reaction. Okay. So some reactions take energy. Okay. If you put calcium chloride, it's not even a reaction really, it's just dissolving it. Calcium chloride, when it gets into water, turns really, really cold. So that's endothermic, takes energy. That's another signature feature of these reactions, okay? Taking in, absorption, or releasing of energy. Okay? You saw all those reactions were pretty spontaneous, but not all those reactions have the same speed. Okay? So we called this kinetics. Okay, so it's related to kinetics and thermodynamics. Put it in your own terms. Okay? They occur at various speeds, but write it. Let's watch the next video and see if you can make observations. This is, I forget which Big Ten school this is, but one of the Big Ten football teams is, their colors are blue and white. I always forget which one it is. Okay? But this is their, okay, schools have mascots. This is the mascot of that Big Ten school. Okay? Ready? So watch what happens here.
The reaction is repeated without stirring. As a result, the color oscillations are not uniform throughout the mixture. The color change appears to move through the mixture like a wave. The formation of gas bubbles also oscillates.
So their fight song is timed to this reaction. Okay, literally. Okay, time to this reaction. What does that tell you? It literally oscillates at a very specific speed. No matter how much of it you mix together, it always has the same speed. Okay? This is called the iodine talk reaction. You can find YouTube videos on this one too. Okay? It's tough to get it to work right. You need really clean glassware and such. Read 6 and tell me put that in your own words. Is there a nice one-word description for that? Or how could you remember that? Because how can you make it speak to you? Definite proportions, definite proportions. Ratios are always the same. Okay, that'd be one way to say it. Stoichiometry. Okay, here, 1 hydrogen plus 1 oxygen always gives you, is that right? How many hydrogen are needed for how many oxygen? So 2 hydrogens for every 1 oxygen makes water. Okay, and then the last one, again, is various extents. So reactions, some reactions go to completion. Some reactions oscillate back and forth. This talks about a little bit about equilibrium. Okay, so this is also a signature feature. Not all reactions are the same. They react to different extents. So let's create a model, right? Let's focus first on what proportion of reactants and products are involved. We'll then use our model to see if we can talk about energy produced or needed. Okay, stoichiometry, thermochemistry, kinetics, and thermodynamics. So we're going to focus first on equilibrium. So this is where we're going to start with our model. We're going to say step 1, mass has to be conserved. Okay, we talked about that before. Number 2, chemical processes always result in change in energy. Number 3, speed depends on temperature, and not all reactions go to completion. Those are those 4 principles. Let's look at the assumption number 1. Chemical reactions, okay, that make up the reactants are rearranged, okay, to form new substances. So let's look at an actual process. So let's look at burning methane. Okay? So, how many people are comfortable with this representation? Burning methane. Okay, you've seen CH4, the state gas, plus oxygen in a gas. Have you seen this before? Could you balance that? Okay. How many people are comfortable with this way? By the end of the class, I want you to get comfortable with both. Okay? If you're very comfortable with this, great. Use it to constantly look at these pictures and diagrams and think about it this way, because it's going to really help your understanding of processes. Okay? So if I were to burn methane, CH4 and O2, let's look at the products that you get. Okay? There's carbon dioxide here. Is it that one? Is it that one? Is it that one? Is it that one? That's carbon dioxide, okay? Black with 2 white balls, red balls around it. That's carbon dioxide. Where's the waters? Right here and here. Okay, I want you to look at both representations. So, now, when you're balancing this chemical equation, okay, how many CH4s do you need in this reaction? Okay, let's say 1. Now, how many O2s? It says 3. Oh, I heard a 2. Why 2? It's only 4 oxygen atoms in here. Notice that in this representation, you can look at these 2 and what are those? These are oxygen. It's on the starting materials and the products. Okay? So what could you say about oxygen in this reaction? How much of it is there? Excess. Yeah, there's excess. So, what chemical in this reaction is limiting the product that you get? The carbon, the CH4. So CH4 is the limiting reagent. Okay? The amount of CH4 here limits how much of the product you can get. So if I were to balance this and this can be ignored, and now just look at the particle representation. So 1 CH4, 2 oxygens gives us 1 CO2 and 2 waters. Everybody okay with that? Okay. You need to have those stoichiometric coefficients there to balance the equation, to make sure you show that mass is conserved. Everybody comfortable with? I'm thinking this is pretty much a huge review for everybody. Okay? Just get comfortable with the particulate model representations above. When you're doing this, there's going to be something in excess often. Okay, oxygen is excess, CH4 is the limiting reagent. What about this one? So look at this particulate representation. Does it help to turn off the lights in the front, or does that hurt? Should I turn out the lights in the front? Is there anything in excess? If I came with index cards that had bonus points that you could collect if you said the correct answer, would that help? Methane. Yeah, methane's in excess. There's 2 molecules, one on each side, so that's in excess. So the limiting reagent here is oxygen, yeah. Okay, so can you write out a chemical equation for this one? Megan, you want to throw it out?
For this one, it would be 3CH4 plus 4O2 equals 4H2O plus 2CO2 plus 1C.
Perfect, except for that last bit. Remember, it's on both sides. So the one that's excess, we'll just ignore it. Yeah, so that's a good lesson. The one that's in excess, it's on both sides. It'll cancel on both sides, so you can cancel it out. Okay? So the first thing you can write about rules here is cancel out what's on both sides that is excess. Okay? And then count them up in order to okay, so there's that methane that's in excess. So did you notice that, so you said 2CH4 plus 4O2 plus 2CO2 plus 4 water, right? So the last step is divide them out to get the lowest common denominators. And what you would see is that these reactants always react in the same way to form the same ratio of products. Okay? So whether it's 1 CH4 or 2 CH4s, 3 CH4s, a mole of CH4s react with 2 moles of O2 to give us a mole of carbon dioxide. Okay? That's what those coefficients mean. So why does mass remain constant? Can you say it in your own words? Who can tell me? Why does mass remain constant? Yeah. Teresa?
The number of particles stays the same.
The number of particles on both sides stay the same. Yeah. You're not changing the number of particles. You're just changing their connections. Okay? So chemical reactions just change the connectivity from the start to the end. Okay? You could say, put it in your own words, but basically, backwards instead of forwards. You know, it's a rearrangement of atoms in the new molecules. Mass does not change because different atoms, okay? All of the atoms stay in the system. How about this example, which is the last one I think that's not in your page. After this, we can go back to the worksheet and solve these in your groups. What about this? So when you're starting here, what's that? Write down the steps. This is a chance where you've done it a couple times. So write down the steps. Okay? Leave notes to yourself at the start saying, to solve these problems, this is what I do, because this is what you're going to forget. So when you're given particulate representations and you want to write a balanced equation, what are the steps? What's one place you can start? Anyone? There's many different ways to solve this problem. Cross out the excess, sure. Okay? So what's excess? So the yellow is sulfur, and this is hydrogen, and this is hydrogen, this is oxygen. It looks like 2 sulfur, 2 SH2s. This one and this one are excess. Okay? So those are in excess. So cross them off on both sides. Or just ignore them. So what's the next step you're going to do? Sorry? Write out the equation which requires you to count molecules, and translate the colors into what they are. Okay, so again, yellow, sulfur, hydrogen is white. So H2S, how many of those are there? 4, right? Because we ignored 2, they're on both sides. Plus how many of this one? So what's this? O2, and how many of those? 6 O2 gives us, what's the product? Notice they're rearranged. Here's an oxygen with 2 hydrogens, here's 2 oxygens with 1 sulfur. Okay, so SO2, how many SO2s are there? 4, and how many water? 4. Okay? So, are we done? 4 plus 6 gives us 4 and 4. Simplify. Last step, simplify. Right, simplify. Great. Yes, last step, simplify. Lowest common denominators. 2 plus 3 yields 2 and 2. Because this would be really long if you had to actually sit and count out a mole of these. Right? Okay. This one's on your sheet, so I'm going to let you do this in your group. Practice your rules. Use this to write down your rules, refine your rules of doing these kinds of problems. We'll walk around and help. But your goal, again, tasks, identify reactants, identify products, identify limiting reagents, balance. So write out these steps so that you'll remember later. Remember, the black ones are carbon, the red ones are oxygen, yellow is sulfur, white is hydrogen, blue is nitrogen. How well are the rules working? Jeffrey, right up. Feel free to jump to the next problem. If you're super speedy, and already solved this one, go to the next one. If you've already got the next one done, if you already have the next one done, you can move on to a much harder representation, which we'll talk about together. finish 10, what I would like to ask is I want somebody to walk me through 11. I want somebody to tell me what I need to do to solve 11. So that's what we're going to pick up. Start bringing colored pencils for the rest of the semester. Or pens. Blue, red, yellow, black. Would really help. Pink and purple are fun too.
I was like, how am I supposed to know?
Yes, all the information's there.
Yeah, I'm like, what's it gonna be?
We have so much more places. It's just hard to ignore it. Yeah. Okay, there was a nice lull in the conversation, so let's, anybody want to volunteer their answer for the equation, if they could read out the equation for number 9? Anybody want to read out the answer for question 9? Just so we can double check. Or is everybody confident with number 9? Anybody have a question? All right, skip it. How about 10? Everybody good with 10? Any questions? No? All right, how about 11? So 11, what is the process you have to do? How do you have to change your list of steps? You don't have to? Okay. So, yeah, sure, you might not have to at all. So what's sort of the process that you went through here with number 11? Are there any questions there, or are you just getting to it? Okay, let's just keep working. Let me just make one last statement. This packet isn't due, it's just the very last page. Okay? So the first 4 pages would have been like the video worksheet, and the very last page where it says D25 is what you'll turn in on Monday. Okay? So keep working. We've got 10 more minutes. It's great. We need to finish the discussion sheet. The only thing I'm going to add, which I forgot, is I added it and then I printed the old copy. So question number 1, on the very final 5th page, if you could just flip to that for 1 second. Question number 1, balance equation, but I'm going to challenge you a little bit further. On the back, draw the particular models. Okay? So for question 1, there's 3 reactions that say balance. On the back, if you would, please draw out the particular models in the boxes, just like the others. Okay? Because I think that would be good practice. Just for question 1, yeah. Okay? So we're going to keep walking around helping and answering any questions you have.
Yeah.
No, there's 18. There's 18.
Because I'm trying to. Yeah. Okay. Yeah, I know what's going on. So what you can actually do is this is Abigail and this. This is actual. Yeah. So what you can actually do is so there's four carbons, right? That you have. Right. But then you end up with two on the side, right? So then you end up with 8 hydrogens.
No. But there's 18 on this side. There's 18.
Not counting. Yeah. Don't count that.
Oh, okay. I think it's there too.
But it's not going to count the reactions.
Yeah, and then to, but then to cancel it out after. Okay, so it's not
Then actually
and 5 out of 10. Yeah.
But there's still not the same amount of time.
Okay.
For another 12 here and then 8 here.
I have 12 and 12.
Oh, you're right.
Yeah.
Oh, yeah. I wrote 4. Yeah, same thing. Somebody
Six H2O, 4 CO.
I wrote C2H4.
Oh, just slightly.
Yeah.
How I got to that, I have no idea. Okay, I basically just wrote everything out that's here, and then you, at the same time as you ignore this thing as excess, you kind of have to like take into account that like it is excess, so you ignore it on the side because you're like, oh, you need that and another extra for this side of the equation. And that's like the easiest thing to start with, and then you figure out what you have left over that you have to balance it out. You know, because like this part is given, like this you get from just looking at this and ignoring this. And then you just figure out what left over you need to balance it. You know? Because like this gave you, like, for as of now when you get to this step, because you know that like if you figure this would be the excess line, you know that you, I think it's in
Because there's an extra.
Okay, that's time. I don't want to. If you want to keep working, there's no class in here after, so you're welcome to stick around. The class isn't in here on Friday, so you still can stick around if you don't have class and keep working. But we're going to take off. Thanks, guys. Have a wonderful weekend.
Wait, the discussion sheet is not due right
Discussion
now,
25 is due Monday in class. We're going to get to class on Monday. As soon as I have the sheets out for 26, I'll have it posted. It's a video with the PowerPoints. There's no video to watch for Monday, okay? So just focus your energy on finishing D25. Have a great weekend, guys.
You too. It's really